Hello everyone, welcome back to the latest lecture session. We just have 2 more sessions to go before we complete this marathon course. Let's dig right into it. In the context of water and wastewater treatment, we are looking at sludge that comes in from different what do we say levels of treatment, primary, secondary treatment and so on and so forth. So, we are looking at residual management. In that context, we looked at or started looking at stabilization, and the method we were looking at was anaerobic digestion. Anaerobic in the presence of, or pardon me, in the absence of oxygen, right. So, we looked at the relevant aspects and we were looking at alkalinity and why that is necessary. We can see that we are going to have acetic acid being formed typically, CH3COOH, acetic acid. Acetogenesis, this was one of the steps in anaerobic digestion, right. First hydrolysis, pardon me, and then you had acidogenesis, yes, where you have the intermediate volatile fatty acids typically being formed, and then you have the acetogenesis, acetic acid being formed, and depending upon the type of the parent compound, you will also have hydrogen being formed, right. And in that context, we saw that these 3 steps typically, or the microbes that what do we say lead to these kinds of steps, acetogenesis, thrive and grow faster than the one that removes what is this acetic acid, right, from your particular solution. So, that was the 4th step, that is relatively slow, is methanogenesis, right. And so, if this acetic acid is not being removed via acetogenesis, as you can see, it is an acetic acid, its pK is 4.76. So, it can bring down the pH, I mean depending on the concentration, from the neutral pH to maybe 6 or so. And as we looked at in the previous session, we know that methanogens, which are the key to this process, right, are going to feel the effects or adverse effects when the pH is 6.5 or so, right. So, you want to control this particular anaerobic digester turning sour, right. We do not want this digester to turn sour, that is one aspect to keep in mind. And here I guess that is where alkalinity comes in, as in acidity to neutralize an acid, ability, pardon me, to neutralize an acid. So, in general alkalinity, I guess we did talk about this earlier if I am not sure, but let me just write down the equation. I am writing down the relevant bases that will come into play if we are titrating usual waters or natural waters from the relevant pH to pH of 4.5 or around 4.5, that is the standard method definition. And because these are the usual bases that you will come across, that is why we have these. If there are other bases that can neutralize the acid in this particular pH range, then you will have to add those bases too. Anyway, so as you can see, if the system is typically around pH 7, you can neglect these 2 and you can neglect this 2, and you will see in general alkalinity will be more or less equal to HCO3 minus. So, what can HCO3 minus do? It can take up the relevant proton and go to H2CO3, let us see, right. So, thus there is no free H plus in the solution, pH is not affected. Another aspect to keep in mind is that during the methanogenesis, you saw that methane or acetic acid can be converted to carbon dioxide. This carbon dioxide, when it is dissolved, right, it will be in equilibrium with H2CO3, and depending on the pH of the solution, this H2CO3 will again be in equilibrium with HCO3 minus by releasing the H plus. So, by releasing the H plus again, due to the production of CO2 that is still in the not the gaseous, in the aqueous phase or dissolved in the aqueous phase, you are going to have or affect or bring about a decrease in the pH. So, these are the 2 aspects or ways that the pH can decrease. So, thus how will you control? By having a good balance between acetogenesis and methanogenesis, right. That is why you need skilled operators for anaerobic digesters. Typically, most anaerobic digesters that fail, at least in India, fail because of poor plant operation, right. So, as you can see, it is not just I can put it out there and like it is not like I turn on a switch and the fan keeps running, right. These are microbes, living organisms, and you need to cater to their needs, that is the aspect. So, one way to look at this is that you will have to sparge it or let the carbon dioxide that is accumulating or that can accumulate, right, So, this will be in equilibrium with carbon dioxide in the gaseous phase, right. So, that has to be removed. Then you will have less carbon dioxide that can be dissolved in the aqueous phase. If not, your pH will decrease. So, that is one aspect to keep in mind, right. So, let us move on from here. So, when alkalinity is less, you will have to see to it that the pH does not drop too much. How can you do that? By adding alkalinity extraneously. So, how can you do that? Either add Na2CO3 or add lime, let us say, right. So, that is the way to go about it. So, as you can see here, we have two aspects here, carbon dioxide in digester gas, right, and then we have the relevant pH here, and also bicarbonate or alkalinity measured as CaCO3, let us say, right. So, that is one aspect to keep in mind. So, as you can see, there is a narrow range where the three variables of interest operationally, carbon dioxide in the digester, pH and alkalinity, right, will be optimum for our anaerobic treatment. As you can see, 6.5 as we mentioned was one particular limit for the microbes before which the microbes will not be adversely affected, and then obviously too high a pH 2 it will not really work out, right. So, again you can see that it is a narrow range out there. So, characteristics of methanogens, as we mentioned, prima donna. So, I will just summarize what we have already looked at. Slow growing, very sensitive to oxygen. Some anaerobes, even though there is oxygen, I guess can, if they are facultative, maybe they should not classify them as strictly anaerobic, right, but there are obligately anaerobic, right. So, those even if you have some oxygen, that is going to affect their system. So, they are pretty sensitive to oxygen. Sensitive to toxics, which toxics? We will look at that soon. As I mentioned, they have a very narrow range of pH within which they can thrive, right. That is one aspect to keep in mind. So, let us look at one anaerobic digester. Here it is a what do we say, floating cover, right, it can move up and down. So, here I guess they have compressed gas lines for mixing. This is the anaerobic digester, right, and it is underneath the ground here. Yes, that is one aspect to keep in mind. So, cross section provided by MIT OpenCourseware from Reynolds, if I am not wrong. Yes, from Reynolds book. So, let us see what it is that we have, right. So, sludge comes in, right, sludge is coming in, sludge inlet pipes, sludge in, that is one aspect to keep in mind. So, what else? I will have formation of my relevant gases. So, let us see where the gas is being removed. So, first they have a gas dome and then they are having a supernatant gas here, right. So, that is one aspect to keep in mind, supernatant gas line here. And here as you can see, it was a floating cover system, not a fixed dome or such, floating cover system, and you can see that it can move up and down in this particular in the vertical direction. And obviously, you have to remove the digested sludge out from time to time, that is again based on the mass balance, and sometimes sludge to recycle, I guess, right. You have to maintain the relevant thickness of your what do we say, anaerobic zone. And again, digested sludge out, this can typically go to the relevant farmland or agricultural land or to your gardens. That is something to keep in mind, right. So, let us move on. The other one, you saw that cylindrical and such, but here some issues are, you can have short circuiting, right, and you can also have accumulation of carbon dioxide here. That is something that you do not want, as we saw earlier. So, a shape of the anaerobic digester which has been seen to practically reduce the downtime or maintenance levels required is the egg shaped anaerobic digester, right. So, firstly this shape, egg shape, prevents short circuiting, and secondly less head space at the top, that also seems to be not only affecting the carbon dioxide or level of control that you can exert on the carbon dioxide in that particular head space. It also seems to be, it is not clear why, preventing foaming or some issues with respect to certain kinds of unwanted microbial growth. So, that is one aspect to keep in mind. Let us move on. So, anaerobic digestion, obviously higher temperature, higher growth, optimal, I guess you see this, and gas production 65% methane and the other should be carbon dioxide. Yes, this is what we see. So, if you are trying to generate electricity or use this for different purposes, you can try to capture this CH4, but if the content or CH4 proportion is very less, then the calorific value of the gas, I guess if I can call that calorific value, will be relatively less, right. So, there are two options, one is you can have or you can burn it and then use it for electricity generation, but you need to look at the costs of running that particular converter, right, and also you have to look at the efficiency of this particular process. Another aspect which I came to know is also being implemented in India, at least in a large scale, is that at the Infosys plant at Bangalore, if I am not wrong, they have this anaerobic digester for kitchen waste, right, not for sludge. And kitchen waste from the methane that is being produced, they are not letting it out into the atmosphere or just flaring it or using it for electricity, but rather they are trapping it or pressurizing it and using it for cooking. At least that is what I remember to have read. Let us move on. So, as we mentioned earlier, we need to be concerned about toxic substances. So, we are concerned about some cations and the concentration is out here and strongly inhibitory range is given here. So, when we are looking at industrial wastewaters by anaerobic digestion, right, even though now we are talking about sludge, depending upon either the type of cation exchanger that you used, right, either if it was mixed with primary sludge, let us say, right, primary sludge at least from water treatment and such, if you are mixing them up, you can sometimes have high concentrations of some of these ions. And as you can see, they can be strongly inhibitory at 8 gram per liter or 12 gram per liter, that is pretty high, but as you can see moderately inhibitory even at 2.5 gram per liter or in that range. And I guess ammonia, nitrogen, you do not want too much of that, right, you do not want this too much. And as mentioned earlier, sulphide, hydrogen sulphide is going to be an issue even at low concentrations. So, you have sulfates or sulfur in your input or inlet, then after reduction H2S will be formed, yes, and as you can see that is going to be strongly inhibitory. So, you will also need to look at the pH maybe to look at the speciation, right. It typically will not be S2 minus, but maybe HS minus, you can try to manage that. As you can see, it is the unionized gas, and then some of the relevant heavy metals. Let me move on. So, types of digesters, low rate, right. Key aspect is it is not mixed, they are layers in digester, digested, digesting, supernatant and scum, as in they are clear layers, right. And that is why, because you are not mixing two, and thus again low rate, higher retention times are required, as you can see 30 to 60 days, meaning larger volume. Other one is high rate with the mixed one requiring lower retention time 10 to 20 days, and two stage I guess where they combine what do we say, low rate mostly for solid separation with high rate. Let me move on. So, biological process. So, we have theta C being greater than theta C minimum at temperature. So, let us look at what we have. So, theta C minimum, let us say if it is 4 days at 35 degrees centigrade, you are typically going to look at a safety factor, and let us say it is 2.5, and then theta C that you are going to use is going to be 10 days. But typically the minimum for digesters is typically 15 days, especially or in general for the heated digester. So, as you can see, the slow safety factor that typically people end up using is relatively high enough, right. So, if you are operating it at theta equal to theta C, right, theta equal to theta C, but you can operate by settling and removing liquids so that theta C is greater than theta, right. So, that is one aspect. As you know, it is all about recycle, and you can manage the operations such that theta C is greater than theta. And we were primarily concerned, or one of the objectives of stabilization or residual management was about pathogens, and pathogens different ways. You are not going to create the environment in which they can thrive, right, and one of the ways is that you will increase the temperature or make it uncomfortable, if I may say so, for them. So, 35 to 55 if the theta C is greater than 15 days, if it is low temperature then theta C we are looking at a longer retention time, right. Volatile suspended solids reduction typically relatively high enough, 40 to 60% let us say, right, and it is highest for solids with low theta C activated sludge. Okay, some of the aspects here, this is similar to, or these variables we have seen in the context of aerobic treatment too, when we were looking at activated sludge and such in wastewater. So, solids yield, right, yield as you can see, let me see, okay, for fermentation 0.06, for methanogenesis as mentioned slow growers and such, as you, so you can see that it is relatively less 0.02 per gram of COD. Compare that with what you have for fermentation. And decay coefficient, right, here we are talking about decay of the volatile suspended solids, right. Let us see fermentation and again methanogenesis. Again, as you see, this is relatively faster, relatively slower. So, that is something to keep in mind, because you want to balance out the amount of acetic acid that is being accumulated, right. And then specific growth rate and such. I would like to compare that with the one for aerobic systems. Let us see what we have. So, design parameters for aerobic digesters. Maybe I should have presented the one for activated sludge process, but that is fine. So, yield, I guess you can see, is much higher, 0.4 to 0.8, right. And again here it is per milligram of BOD. Maybe for COD it would have been slightly lower, but that is fine. You can see that here the yield is 0.06, and here we are talking about yield around 0.4, let us say, right. And I guess what else do we have? We have Ks, and that too I guess you can see is relatively much higher, right. And decay 0.06, let us look at what it is. But in the context of decay there in the anaerobic digestion too, I guess we will have to look at another aspect there, but I will mention that when we are looking at decay. Where is this? Decay is here. Again you see it is maybe relatively higher again, right. So, again as you can see, typically anaerobic process are relatively slow, and that is what I wanted to mention. Firstly, they grow slower, and also even the rate constants are slower, let us say. This is capital Ks here, right. Okay. So, let us move on. The range of physical design criteria for high rate anaerobic digester. Typically now in India, people are pushing for high rate anaerobic digesters. So, let us see what it is that we are typically looking at. Diameter 6 to 40 meters, but rarely will we go to 40 meters. Typically 8 to 10 meters is fine, and 6 to 15 meters fine. Again, slope for gravity withdrawal of your relevant sludge, and the level of mixing and such. If the gas is unconfined and confined, yes, these are the aspects. So, sometimes you will have to heat it, but in India, because of the relatively what do we say, warm ambient conditions, heating is not required there. So, that is one aspect to keep in mind. And gas production, if you are concerned about how much gas you are going to produce, it is going to be 0.75 meter cube per 1 kg of the volatile suspended solids, right. So, evaluation, just let me start summarizing from here without going into the details. So, one aspect note is our objective, which is the biodegradable organic matter should be decreased considerably, and that is what we see here. And operational costs low if the gas itself is used, especially for mixing or for energy generation. It is applicable to a range of wastes, and the relevant stabilized sludge can be used for agriculture, right. And as mentioned, because of the temperatures that are going to be maintained, typically you are going to have good pathogenic inactivation. And obviously, as you see, it is an anaerobic process. You are not providing energy. At best, you need energy for some level of minor maintenance, or for mixing if you are going to go for the high rate anaerobic digesters. Even that is not a lot, right. So, as you can see, the key aspect is low net energy requirements. So, one aspect though is that you know, they are prima donnas, right. You know, you need to really cater to their needs and look after them. So, that is one aspect, or if I should say not disadvantage, one concern that you should be looking at, especially considering the lack of skilled manpower. So, disadvantage, let me what do we say, summarize them. As I just mentioned, skilled manpower is required, can sometimes lead to foaming and sour digester. This is what we talked about earlier with respect to pH dropping and such. And once it turns sour, or there is an upset in the, or the microbes are upset, right, and then it takes a lot of time for them to recover. So, that means your plant is not going to operate as efficiently. So, it is a very fine balance, that is something to keep in mind, right. And another aspect is the supernatant is considerably strong. If you recycle that, and again what do we say, if you recycle that to your activated sludge process, for example, we have activated sludge process, let us say, okay, and this sludge we are taking to our anaerobic digester, okay, let me say the egg shaped one, okay, and you are going to have supernatant, and if this supernatant you put this up here, right, again it is all about mass balance, right, how much organics are coming in and so on and so forth. So, if you put this in, because it is such high strength supernatant, it can interfere with the activated sludge process if you not designed well. So, cleaning is difficult obviously, and initial cost is high. For example, for kitchen waste, let us say I am just talking about some rough numbers. For IIT Roorkee, kitchen waste around 3 tons, or kitchen and relevant waste, organic waste estimated to be 2.5 tons or 3 tons for the 16,000 population, let us say. And for that I guess if you can get it relatively at a fair price, the system anaerobic digester system will be around 60 lakhs or so. So, that is one aspect to keep in mind, right. So, safety of combustible gas, as in if you are flaring it or using it for energy or for compression for using in the mess or such, that is one aspect to keep in mind. Obviously, odors, if you let the methane or such or some of the anaerobic gases out. So, that is an aspect, let us say. And straw white, this is one particular compound that can precipitate out and can lead to issues. So, that is another aspect to keep in mind. So, let us move on. From now I will mostly start summarizing it, because these are aspects, at least the principles of aerobic digestion. If not for digestion, for aerobic aspects and such, we looked at the principles. So, from now on I will mostly be summarizing the aspects. So, what are we looking at? It is, as I just mentioned, similar to the activated sludge process, let us say. Obviously, if it is aerobic, I need to supply air, right, and then after that I am going to look at sedimentation, where I form the relevant flocks, let us say. That is why it is an extension of the activated sludge process. So, supernatant, which is not of typically very high strength, which is one of the advantages of this aerobic digestion, goes back to the head of the plant. When I say it is not high, it is not as high as that from the anaerobic digestion, that is what I say that, but in general too it is obviously going to be high compared to the effluent from the activated sludge process, right. Here we are talking about effluent from the anaerobic digestion, right. So, if I not aerobic digestion. So, if this is my typical activated sludge process, right, and this is being recycled, and if for this sludge, or if there was a primary what do we say, sedimentation zone even for wastewater, and I am also collecting that sludge, and I have another activated sludge process here for this, right. So, this particular supernatant is going to be higher in strength compared to this particular effluent here. So, I can recycle this back here too, but again you have to be concerned about TKN and total phosphorus. So, treated sludge is around 3% solid, that is one aspect obviously. When do we use it? Typically when our major goal is to reduce pathogen and prevent attraction of flies and such, and 30% reduction in VSS, not great, but well workable. But obviously what is the issue though, right? The issue is that for an aerobic process you need to provide oxygen. So, that means it is all about money, right. So, you need to provide air, meaning pumping costs, right, that is going to be considerably high, especially because the concentration of your relevant what is the sludge or the organics that you are going to degrade is going to be pretty high. Though the flow is going to be less, the concentration is going to be pretty less. So, microbial process, let us say this is general formula for the cells. So, to balance it out, what do we have? We need 5 moles of oxygen for this generic formula of the relevant cells, let us say, right. So, it is 1.42 kgs of oxygen, right, 5 molecular weight of oxygen, and 113 looks like is the molecular weight of this particular compound, which we are using to represent the cell mass per kg of volatile suspended solids. Anyway, 1.42 kg of oxygen per kg of volatile suspended solids. If nitrification is also allowed to take place, first for nitrification, right. So, let us see what we have. We are going to require considerable amount, this we saw even in the activated sludge process, 4.57 kgs of oxygen per kg of NH3 or NH4 plus, let us say, right. So, that is something to keep in mind. So, it is around almost 2 kgs of oxygen per kg of volatile suspended solids. And as you can see, I guess especially when you are having nitrification and relatively high ammonia content, it can result in low pH, again affecting the microbial growth, especially if the alkalinity is low, right. Let me go ahead and start summarizing aspects. So, here we are talking about degradation of volatile suspended solids itself. In the activated sludge process, we were trying to promote the growth of these microbes, which we were trying to measure by VSS or MLVSS, right, mixed liquor volatile suspended solids, to degrade your what is it waste or my waste, right. Here The waste itself that I am concerned in degrading is this microbial, what do we say, microbes, which I am going to measure by volatile suspended solids. So, I am concerned with decay of the volatile suspended solids. So, that is what I have. So, this has to be a small k. Rx is equal to minus Kd into x, x is the concentration. So, if it is for CSTR, simple balance and such, you can get the relevant equation, let us say, right. And typically looks like we are looking at 30 days of retention time. Okay. So, general values, but key aspect is that temperature, but in India because the temperature is relatively warm, that is why you see that the constants are relatively higher, and that is why even if the plant operation is relatively poor or such, we can get by. But in most of the European or Northern American or Southern American countries, the temperature is more or less in this range if not lower, and their plant operation and such becomes a key requirement. So, as we can see, oxygen requirements, one for the cell tissue. So, here I guess they are talking about 2.3 kgs of oxygen per kg of VSS destroyed, but obviously it depends upon the type of formula that is used. For the one that we use, we got a different number, right. So, oxygen concentrations around 1 milligram per liter, and then waste activated sludge and so on and so forth, but I will skip these aspects, let us say, right. So, mechanical requirements, as you can see, requirements are typically for aeration and or mixing, let us say, right. So, this is the key aspect which drives the energy costs, and the other aspect obviously is the depth for diffused air and the circular diameter. As you can see, concentration high and such, high retention times, I think theta was pretty high as we saw, that is why the dimensions are going to be relatively higher here, right. So, let me move on. So, this is what a typical one looks like. Let me see the information that we have here. The soil's concentration must be controlled, that is something that we always know. Concentrations above 4% will impede mixing, and adequate dissolved oxygen levels might not be maintained, let us see, if the soil's concentration is too high, that is something to know, right. So, these are general aspects. Again, this is an aerobic digester, not a typical activated sludge process. So, you see the airline, waste activated sludge that coming in for recycle to maintain the relevant microbial activity at the relevant concentration. So, evaluation, what are the typical advantages? Relatively low initial cost, it is all relative, and one advantage is compared to the anaerobic digester, the supernatant is weaker, relatively simple operation, right, and again activated sludge process widely used and adapted, applicable to considerable range of waste and odor control, is easy, and we can reduce the sludge mass, let us say. But disadvantage, obvious issue is that, as I have been parroting since quite some time, it is remarkably high energy cost, and compared to anaerobic, as mentioned earlier, the VSS degradation is going to be relatively lesser, let us say, right. And these are aspects that are always coming into play with respect to pH and alkalinity decrease. And one other key aspect here is, unlike the anaerobic digester, which is relatively closed, aerobic digester, you have it open to the atmosphere, and you are pumping what do we say, air through it continuously, right. So, there is an exchange with the gaseous phase, and so pathogens can be spread by aerosols, that is one aspect to keep in mind. And looks like it is difficult to dewater later on, relatively difficult to dewater, and cold temperatures, as with any biological process, are going to affect the performance. And we also looked at some of the foaming related issues when we have high, what do we say, or depending on the type of FBM, we have different foaming related issues, right. And then autothermal aerobic digestion. Let us see what it is. I will more or less start summarizing from here. It is aerobic digestion, it is autothermal aerobic, right. It is aerobic, but thermal too. But we use heat released by oxidation to raise the temperature to 60 to 65. During oxidation, energy is released in that particular process. So, rather than allowing that heat to dissipate, we are going to try to use that heat to heat up the system, let us say, right. So, that is why it is autothermal. High temperatures meaning improved pathogenic destruction, and also I guess preventing nitrification or inhibiting nitrification if required. So, what do we need? We need higher suspended salt concentration, and typically it looks like we have the minimum is around 30 gram per liter, meaning COD is around 40 gram per liter, let us say. So, that is something to keep in mind. 40 gram is 40,000 milligram per liter. Now, you get an idea about the high concentration that is needed, let us say. And obviously, if I am trying to retain the heat, I have to insulate the digester, right. and because of the higher temperature kinetics are faster, and that is why retention times are relatively lower. And efficient aeration is required. Why? Because I do not want the heat to escape along with the air leaving the digester. So, again relevant aspects come into play with respect to design and the relevant operation. So, let us quickly look at the advantages. Retention time is relatively lesser. Why? Temperature is higher, volume is reduced. Obviously, if the kinetics is faster, the retention time lesser, then theta is equal to V by Q, again the kind of the volume is going to decrease, let us say, right. Excess heat can be recovered, and pathogen reduction because of this excess heat is going to be pretty good, let us say, right. And disadvantage, again high energy costs, depending upon how well you are running it, again foaming is an issue. And as mentioned earlier, skilled operators, right. Why? Again you are talking about trapping the heat that is generated, having a high strength what do we say, waste in there, right. Suspended solids concentration is such that it is around 40,000 milligram per liter in terms of COD. So, you have to maintain these aspects, right. So, let us move on to different kinds of what do we say, composting now. Again we are still in the context of stabilization. In stabilization we have looked at anaerobic, aerobic and aerobic, where the heat is reused again, and here we are talking about composting. Composting, you would have heard that a lot. Let us see what it is about. So, aerobic, autothermal digestion of dewatered solids, fine. And what is it that we are talking about? We have complex organics, you are going to provide oxygen, and then they are going to degrade to relevant oxidized products, right, carbon dioxide, NO3 and such, and less complex organics, and heat is also given out. That is why I guess it is autothermal, let us say, right. Optimal temperatures 50 to 60, we need aeration, right, and if we are aerating it, right, again this is composting. You would have heard of different kinds of composting, especially with solid waste management or the waste from your kitchens and such, let us see. So, if I am providing air and if my particles are pretty small, right, the air will not flow through it. You do not have the voids or interconnected voids for the air to flow through it relatively freely. So, that is why you are going to provide bulking agents. So, what is it that we typically add or can add? Wood chips, ground lumber, leaves, shredded tires and such, let us say, right. And after screening later on, the bulking agent or part of it can be recovered. So, that is one aspect to keep in mind. In general, for composting, if not for sludge, at least if you are trying to compost it in your homes, what is it that you need? Depending upon the type of waste, the key aspect is to maintain a ratio between the carbon and the nitrogen. Primarily, most what do we say, waste that you are trying to compost, the process fails. I guess here we are talking about both the digestion in the R context and also composting of your solid waste, let us see. They fail because there is not certain sufficient carbon to nitrogen ratio. As you know, the microbes need carbon and nitrogen in different quantities. So, if one of them is missing, let us say nitrogen is too low, carbon is too high and nitrogen is too low, or if your carbon is too low and nitrogen relatively compared to the requirement is too high, right, then microbes are not going to thrive. So, here it is a mixture of adding a source of carbon if required. Typical source of carbon can be dry leaves and such, which they call as brown matter, and nitrogen is typical organic waste from your kitchens and such. So, if you have a good enough ratio, and then you can aerate it well, and also you need to seed it, as in where are the microbes going to grow from? They can grow from what is in the nature, but then it is going to be too slow. So, you can add some seed initially, right. So, that is these are the relevant requirements: carbon to nitrogen, temperature, oxygen, moisture control too high and it will fail, too low and microbes won't thrive. If the moisture is too high, again you are going to have issues with respect to the what is this temperature that is being maintained and such, as we can see here, right. And oxygen, these are the relevant aspect, and obviously seed, this is for the kitchen waste. But for sludge from secondary waste, do you need seed? Not really, because most of the microbes, I mean you have microbes depending upon the age of that sludge. So, let us see what else we have here. But one aspect is initial soil concentration of mixture is 40 to 45%, let us say, right, that is a high requirement. So, aerobic stabilization, here I am showing the pictures for solid waste management also, because I think that is relevant in our context, right. It can be different kinds of food waste, yes, and after this all this will come into this particular form which is relatively more stable, right. So, this is the composted organic, let us say, right, which can be reused as fertilizer or such, or for gardening, depending on what kind of waste you are putting in, let us say, right. That is one aspect to keep in mind. And in general we have a thermophilic phase and a mesophilic phase, right. Here we have two stages, one is breakdown of proteins, fats and cellulose, and the other one mesophilic, which is relatively long and slow, let us say, right. Lignin remarkably difficult to degrade, I guess, right, and those are going to be taken care of in this phase. So, typically you have 3 phases, but it is a repetition of 2. So, mesophilic initially rapid uptake of soluble sugars and starches, right, that is why you have explosive growth initially, right, and then you are going to have thermophilic phase, and here you have thermophilic bacteria and acetinomycetes and the most heat tolerant fungi. Why? Because as you can see, considerable heat is generated during this aerobic composting, and that heat will see to it that or will ensure that the pathogens are going to die, and obviously only those kinds of microbes or organisms that can resist that heat will thrive in that. So, again temperature is a key requirement here in going from one phase to the other. So, water content, as I mentioned, is critical. If it is too high, poor aeration and temperature will be affected. If it is too low, then you are going to have microbial activity that is going to be very strongly affected, right. And let us move on. Okay, looks like I am almost out of time. Let me finish up this composting and we will move on to the next session. So, time period, what is it that you are typically looking at? So, 30 days, that is a considerable lot. So, without aeration after composting, that is going to be 21 to 28 days, relatively later. Challenge, obviously odor. So, if you are going to have composting what do we say in your surroundings and you do not take care of your process, so that can lead to odor, let us say, right. So, that is one aspect to keep in mind, and that is why even when the solid waste management or the municipality wants to set up composting units in the locality, that is why people typically either with or without knowledge typically push against it, but again with considerable operational control you can prevent odor, let us see, right. So, that is one aspect to keep in mind. So, in vessel composting, that is something that can be done, as in you are going to have a reactor, as in it is in vessel not open to the atmosphere, which can be aerated and it can be moved or such that it is either a plug or mixed, depending on how you are going to what do we say maintain it or design it. If the temperature is too low, right, if it will affect the degradation and it will also lead to odor, let us say the kind of microbes that are going to thrive when the temperature is too low, it again can lead to odor problems, right, and thus again aeration and relevant control is required, let us see. So, here you have different kinds of in-vessel composters, right. So, evaluation advantages: improved odor, especially if you maintain it well, temperature control, smaller area, that is a key aspect, and less operator exposure, let us see. What are the disadvantages? High maintenance, material handling limits, the type of bulking agents or materials handling limits, the type of bulking agents that can be used, let us see, right. So, with that I will end this session, and in the next session, which will be our last, we will move on to the aerated static pipe, right. Again, what are we discussing? We are discussing composting the sludge, let us say, or making or stabilizing the sludge, right. So, thank you for your patience.